Hello guys, my name is Arun and welcome to my channel. This is a series of tutorials on terminologies used in high performance computing. Okay, now in this tutorial, this is going to be an introduction. This is going to be an introduction to the idea behind OpenMP implementation in Fortran. So this video will be like the 0th video for my OpenMP tutorials. So if you guys are like, I don't want to see all the terminology videos and get to know about it before jumping into the tutorial or something like that. If that is your case, then I tell you guys that have a look at this video and then you can just if you want you can skip the remaining and then directly jump into the OpenMP tutorial series. Okay, and that's about it. And in this tutorial I'll be explaining you guys the fundamental idea behind OpenMP, namely forking and joining, and about speed up. Okay, here's the thing. So the idea behind the OpenMP is as follows. Suppose if we have a code like this, okay, code like this, and you divide this into several sections depending on several sections. I noticed that between sections like 1 and 3 the code is serial and it cannot be parallelized, meaning it has to be done one after the other by a single thread. Similarly, the same applies to the sections between 7 and 10. So in these regions they are serial, so you can't do anything about it. But between regions 3 and 7 the code is parallelized. The code can be parallelized. The region of code between 3 and 7 is parallel, can be made parallel. So in this region is where we can concentrate on using multiple threads, because here in serial parts there's no point in using that. It's not required, so it's no point in using that. Okay, the idea behind OpenMP is this: have a master thread which would have otherwise when run serially will do the operation in a single flow of control, with flow of control represented by this black arrowed line, okay, whichever you call it. So the idea behind OpenMP is find the location where the code can be parallelized. Okay, that will be the starting, that will be this blue point over here and this blue point over here. These regions indicate the starting and ending point of the parallel regime. Okay, and what OpenMP principles says is that in this region split the job among the threads. Simple, meaning instead of this black line taking the flow of this black thread, or this black line taking the line of the flow of control, share the load among the threads under these regions and let them do the job simultaneously. And once you hit the end of the parallel region, push all the jobs to the same thread and let the thread go on in these regions single. So what you notice is that you notice the jobs being split to multiple jobs at this region, and you notice the threads giving the job back to a single thread at this region. So this point where the jobs is being split is called as a fork, and this process of splitting the job among multiple threads is called as forking. And this point where the jobs start to merge to a single thread is called as a joint, and this process of the threads joining or just pushing the load back to a single thread is called as joining. And in these cases the threads that were created over here, they're not actually destroyed per se, they're just being done by multiple processes. And once these are done, the process that were used to do these jobs, they just start doing something else or remain idle, and that's it. They're not going to get destroyed per se. That's about it. So in this program, in this example, you see there's one forking and then one joining. Okay, now if you take a slightly more complicated program, and there are like 16 sections in it. Section 1 to 3 is serial, 6 to 10 is serial, 13 to 16 is again serial, but regions 3 to 6 is parallel, and 10 to 13 is parallel. So in these cases, between 3 and 6 you have to fork and join once, and between 10 and 13 you have to fork and join once, denoted by the red lines over here. This is a parallel regime. This is another parallel. Okay, now let me anyway, what I mean is this is a parallel regime over here, and this is another parallel regime over here. Okay, that's about that's about this part. Okay, now the thing I would like to talk to you guys right now is that is how this is significant to Amdahl's law. Now, what Amdahl's law says is that you reach a particular value of speed up. You just reach a particular value of speed up, or your speed up just plateaus after a particular point, and that particular point is decided by the fraction of the code that is parallelized. Okay, what it means as as follows. Let's ideally, if you your speed up is given by this formula. It's given by the ratio of the time taken for your code to run serially divided by the time taken for your code to run parallelly. Suppose it took like 5 seconds for your program to run serial, and it took 1 second for the entire program to get executed in parallel. Then your speed up is 5 divided by 1, so you can have like speed up is 5. So it's like you increase the time, increase the speed by 5 times. That's your speed up. Okay, sometimes you might want to do this in a different manner, but the time is much more easy to quantify, so it's easy. Now suppose if you have a completely 100% parallelizable code, like you just have the code that can be parallelized from the beginning till the end. Okay, then the speed up will be automatically equal to n, where n is the number of threads used. That is, if the code is 100%, if the code can be 100% parallelized, then your speed up will be completely dependent on your threads. Okay, but that's in a perfectly theoretically ideal case. But on a practical case, your code is cannot be 100% parallelized. There are explicitly regions where your code will be serial. Okay, so in this case, to understand at least in first principle, like how that can be modeled is by usage of a quantity called as f. Now f is the fraction of the code that can be parallelized. Okay, so it's actually a dimensionless value whose value ranges between 0 to 1. Okay, if f is 1, then intuitively speaking, the code is 100% parallelized. If f is 0, then the code is 100% serial. Okay, ideally, realistically, all your codes will have if you look at your codes, almost all your codes will have a non-zero value of f. Okay, if there is any potential to be parallelized. Okay, so what happens is as follows. Ideally, the time taken, let me write this in black. Time taken for your parallel execution is usually 1 times 1 minus f times time taken for your serial plus f times time taken for your serial. F times time taken for your serial part. Now if we add them up, let's say if we add them up, this will turn out to be ts again. Okay, if there is no speed up. Okay, now here's the thing. This time you cannot do anything about this time because this region is the serial part which you cannot parallelize, whereas this is the parallel part. Okay, now let me give this is the serial part which you can't do anything about, and this is your parallel part which you can divide, which you can do. And now here again in this parallel part there are limitations. Like if this parallel part is completely parallel, you can completely parallelize this code. Then if you use n threads, then this fraction of the code will get let me use a different color. This fraction of the code will take f by n times ts. The time taken for this part of the code to execute will be f divided by n times ts, where f is actually the fraction of the code that is parallelized and n is the number of threads you use. Okay, so let's do a small calculation. Let's say ts is like 5 seconds. Okay, and for a particular code f, you have like f is 60.60. That is 60% of the code is parallelizable, and you're using n threads. Okay, n threads. Let's say your n is 4. Now the time taken for parallel is as follows. it is 1 minus f divided by t 1 minus f multiplied by ts plus f times ts divided by n. So if I look at it, 1 minus f is, so this is 0.4 times ts plus f divided by n, so this is 0.15 times ts. So what I get is that I get, if I add this, it's 0.55 times ts. 0.55 times ts. Okay, now if I just take a calculator, 0.55 times 5 seconds is ts, so I get this to be 2.75 seconds. Okay, now your speed up is actually ts by tp, so 5 divided by 2.75, this will be equal to 1 divided by 0.55. if you look at this as this logic, if you look at as per this logic, so what we have here is that 5 divided by 2.75, it's the fraction is 1.818, which is you get like an additional plus 81% speed up. You get an additional 81% speed up approximately. You get, okay, that's the speed up you get. That's for like 60% of your code. That's for your 60% of your code, and that is it. Now suppose let's push this to now this is when you use f is 60% and your n is 4. Now let's do the same case for a different value. ts is 5 seconds. Now f is again 60% or 0.60. Now let's put n equals 10. Now if you calculate tp is 1 minus f times ts plus f times ts divided by n. Now 1 minus f is 0.4 times ts, and if you notice this is the same as we saw over here, and your f by n is 0.06 because 0.6 divided by 10 is 0.06 in ts. So what you get is 0.46 ts, this will be 1 divided by 0.46, 1 divided by 0.46, and if you take a calculator again, 1 divided by 0.46 is 2.713 is 713? Yeah, sorry, 2.173. It's 2.173. Now if you notice this, no matter how much, no matter whatever you do, no matter how much you increase the number of processors, this term will not affect the time taken for over here. So theoretically, if I were to take n to be, if theoretically n approaches infinity, let's say, then tp will approach 0.4 times ts. So my speed up max will approach 1 divided by 0.4. So my speed up will approach 1 divided by 0.4 will approach 1 divided by 4. So my maximum speed, my speed up max is 1.4, 1 divided by 0.4, and that is, if I were to calculate that, it is 1 divided by 0.4, 2.5. So it's 2.5. So the maximum speed up I can get is 2.5, and that's it. So if I were to plot this, let's say, if I were to ideally plot this, okay, with speed up on x-axis, speed up on y-axis, okay, y-axis, and then number of processors on x-axis, number of threads or processors on x-axis. Okay, if I use 0 I won't get any, so if I use 1 I get a speed up of 1. Okay, if I just plot whatever I have, if for 4 I get like 1.818, so this is 1.818 and I get this for 4. Okay, I get this point over here, this point over here. For 10 I get 2.713, 2.173. So I get like this. So this is my 2.5 line, 2.5 speed up line. So the curve will go like this and then plummets down asymptotically. When n approaches infinity, these two will meet, but till then this will asymptotically go, and no matter how much processor you use, you don't get a speed up. And so after a particular tipping point, no matter how many processors you use, the speed up will not increase, and that speed up will not increase. So the only way to make sure that your speed up increases is by pushing the value of f. Okay, and this is called as Amdahl's law. This is called as Amdahl's law. What it says is that unless otherwise you try to increase the fraction of the code that can be parallelized, you can't do anything. You can't increase the speed up beyond a particular limit. So as a condition, no matter how many processors or how many threads you use, beyond a particular point, they won't make sense, and the speed up will just plateau down, and it will never plateau down, and there is an upper limit on the maximum speed up you'll attain. Upper limit you'll attain. On the other hand, if I were to use a different fraction of a code, if I were to use a different value of f, then my curve will be slightly different. My curve will be slightly different, but again this will be like this, because the speed up, at least as per this definition over here, TP is actually 1 minus f times ts plus n divided by f times ts. So this is ts, if I take this common, 1 minus f plus n by f. So your speed up is actually 1 divided by 1 minus f plus n divided by f. So this is actually your speed up, unless you do something about f. You do something my mistake. I did something wrong. I did this wrong. Okay, I did this wrong. I did this wrong. TP equals 1 minus f times ts plus f divided by n times ts. So if I take ts common out, so this will be 1 minus f plus f divided by n. So your gain is, speed up is 1 divided by 1 minus f plus f divided by n. So if you look at it, if n increases to infinity, this term will just vanish, and your maximum speed up is max is 1 divided by f, and in this case, if f approaches 1, then your speed up just shoots up. So on the other hand, if your speed up just improves dramatically. So if I were to make a plot, okay, between speed up and f, let's say, okay, now initially the speed ups, let's say this, I just put this as, when f is this is your speed up is 1 Mach 1, which is your standard benchmark. So when f is 0, it's 1, and gradually with the increase in f, your speed up just increases, and when your f is 1, you see f is 1, okay, all of a sudden you start to get a kink, and then there you go. Your speed up asymptotically increases and will reach almost infinity when f is equal to 1, when f approaches 1. When f approaches 1. This is again Amdahl's law. Amdahl's law. So what you have to keep in mind is that not all the code can be 100% parallelized. Not all the code can be 100% parallelized, and speed up has some kind of major implication because of Amdahl's law, and there are a lot of complications behind it. But on a first principle explanation, Amdahl's law is extremely vital to understand what's happening. So if you want to speed up your code beyond a particular point, the number of process doesn't help, whereas f, the fraction of the code that can be parallelized, so I'll put this in the red box over here, this is vital. Now if you're able to push your code, make your code such that you're able to increase the value of f, that's more important. Automatically when you do that, the number of threads automatically increases, and you'll have a good speed up. Okay, now that's about the basic overview and the idea behind OpenMP, using the concept of forking and joining and how it is related to your Amdahl's law. Thank you guys for watching, and with this video you can just directly jump to your OpenMP tutorials anytime you want, so you can have a look at it. Okay, thank you guys for watching, and I'll see you guys next time.